ill-qualified to be introducing to you the next speaker, Professor Takuro Mochizuki from RIMS, the Research Institute for Mathematical Sciences in Kyoto. Indeed, I only have the vaguest understanding of his fundamental and beautiful work on D modules, and we'll leave the explanation of it entirely to him. I think he'll do a fantastic job. However, I do know that it's the culmination of continuing investigations carried out by the best geometers, topologists, analysts, and number theorists of successive generations, incorporating and unifying ideas of people like Grothendieck, Sato, McPherson, Deligne, Beilinson, Bernstein, Kashiwara, Saito, Brzezinski, Malgrange, Hitchin, Mebku, Sabar, Corlett, and Simpson, just to name a few of the main contributors. I certainly hope not to have slighted any of the numerous other great mathematicians who have done equal or greater work in this area. My main reason for going through that list is it illustrates very clearly the global nature of mathematical research in our times. The numerous channels of communication, collaboration, explicit and implicit, that casually run across the political fiction of regional boundaries as well as the imagined boundaries between areas of research in mathematics. Meanwhile, in addition to Professor Mochizuki's own fantastic efforts, I think it's important to acknowledge the very special environment and culture of Kyoto and RIMS. And I think Professor Mochizuki will agree about this. He received his doctorate there, and from its flourishing tradition of algebraic analysis, his great results have emerged. Anyone who has visited will be impressed by the incredible intensity of creative energy that runs through the spatial temporal corridors of the modest-looking institution, embodying in mathematical form the tradition of sophisticated artisanship and humble devotion for which Japanese industry is justly famous. This wonderful mixture of global awareness and regional creativity appears also in the mathematics itself, since Professor Mochizuki's most famous theorem might be said to locate the difficult analytic source of a decomposition theorem for perverse sheaves that appeared initially to be geometric, maybe even arithmetic in nature. So in every possible way, his work illustrates the pleasant slogan that has developed over the last several decades in our collective move toward a complex but harmonious common world. The slogan I'm thinking about, of course, is think globally and work locally. So please welcome Professor Takuro Mochizuki.
Thank you. Thank you for the introduction. And it's my great pleasure to give a talk here. I thank the committee for the invitation. And I'm also grateful to the staff of the ICM for their excellent hospitality. And I'd like to express my gratitude to my mentors and my colleagues and my friends and my family. So today, I will give a report on the progress in the theory of harmonic bundles and twistor D modules. So let me begin with a classical theorem of Corlett, which says a flat bundle on complex projective manifold is semi-simple if and only if it admits a purely harmonic metric. Let me remind you some terminologies. So complex projective manifold. Yeah. A complex projective manifold is just a compact complex submanifold of a complex projective space. For instance, compact Riemann subspace is a projective manifold. And complex projective manifolds are one of the most important objects in the study of algebraic geometry. And flat bundle is a vector bundle with a flat connection. And flat connection is a differential operator like that, and satisfying Leibniz rule and the integrability conditions. And as well known, flat bundles are equivalent to representations of the fundamental group of the base space if the base space is connected. So they are important in the study of geometry and topology. And a flat bundle is called simple if the connection does not preserve any non-trivial subbundle. And it is called semi-simple if it is a direct sum of simple flat bundles. And general flat bundles are obtained as extensions of semi-simple flat bundles. So semi-simple flat bundles are most basic in the study of flat bundles. And non-standard terminology in this statement is a pure harmonic metric of flat bundle. That is a Hermitian metric of the vector bundle satisfying a compatibility condition with a flat connection. And the compatibility condition is described as a nonlinear partial differential equation, which I shall explain later. And flat bundle with a pure harmonic metric is called a harmonic bundle. And that is one of the most important objects in our study. And let me revert to the theorem of Colet. So if the base space is a projective manifold, then the semi-simplicity of flat bundle is characterized by the existence of pure harmonic metric. And we can appreciate the theorem of Colet from the various viewpoints. Let me mention the following 3 points. First, it gives an amazing relation of 2 completely different properties of flat bundles on projective manifolds. I mean, it relates the semi-simplicity and the existence of pure harmonic metrics. And the semi-simplicity is rather categorical property, and the existence of pure harmonic metric is the solvability of a nonlinear partial differential equation. So they are quite different properties. And let me also mention this equivalence does not necessarily hold for general complex manifold. So this shows a very surprising and rather strange property of complex projective manifold. And the second point is the theorem is an important starting point for further studies. The theorem implies any semi-simple flat bundles are equipped with a very strong structure. And the theorem also implies the modular spaces of flat bundles are equipped with very strong structure. So on the basis of these facts, many interesting research studies have been done. And third point is the theorem is proved with the method of hard analysis. Precisely, it is not so difficult to deduce the semi-simplicity from the existence of pure harmonic metric. It is an excellent observation, but we can prove it by rather formal computations. But for the converse, we need a hard analysis, and it is very deep. And let me show you an easy application of this theorem. So suppose we are given a holomorphic map of complex projective manifolds. And suppose we are given a semi-simple flat bundle on the target space. Then the pullback of the flat bundle is also semi-simple. We can prove it very easily because the pullback of pure harmonic metric is also pure harmonic metric. We can check it by direct computations. But I don't know any elementary proof of this fact without using the theorem of Colet. So this shows a glimpse of the power of the theorem of Colet. And one of the main results in our study is a generalization of the theorem of Colet in the context where singularities are allowed. Namely, a harmonic D module on complex projective manifold is semi-simple if and only if it admits a pure harmonic metric in some sense. Harmonic D module is a generalization of systems of linear partial differential equations, which gives non-trivial constraint at any point in any direction. And it is also a generalization of flat bundle. We can regard it as the flat bundles with singularities given on subvarieties. And there are several reasons to study harmonic D modules. For instance, they are useful in the study of the cohomology group of algebraic varieties. And for instance, in the representation theory, they play the fundamental role in the geometrization of algebraic objects. And for instance, even in mathematical physics, some interesting objects are given in terms of D-modules. So the concept of harmonic D-module is one of the most fundamental in the contemporary mathematics, I think. And as in the case of flat bundles, harmonic D-module is called simple if there is no non-trivial D-submodules. And it is called semi-simple if it is a direct sum of simple ones. And as in the case of flat bundles, our theorem gives a useful and rather strange characterization of the semi-simplicity of algebraic harmonic D-modules. Actually, as we will see later, fully harmonic metric is a concept in differential geometry. So it is rather surprising for me to have such relation with harmonic D-module, which is very similar. And our theorem also implies any semi-simple algebraic harmonic D-module is equipped with a very strong structure. In some sense, it might be an analog of the theorem for purity of semi-simple Palmer shifts on algebraic varieties over finite fields due to Laforgue. So, as I mentioned, our theorem is a generalization of the theorem of Corret in the context where singularities are allowed. So we have to deal with the difficulties caused by the singularities of harmonic D-modules and purely harmonic metrics. So for instance, we have the following issues. First, we should ask what we can show in the study of the singularities of harmonic bundles. Harmonic bundles are objects in differential geometry, but the classical pictures in differential geometry are not so useful for the study of the singularity of harmonic bundles. And the answer is given by a principle called Simpson's meta-theorem, which says any objects and any theorems should have their counterparts in the context of a generalized Hodge structure called twistor structure. I will explain more details on Simpson's meta-theorem and twistor structure, but it implies the study of the singularity of polarized variation Hodge structure can be a useful model for the study of the singularity of harmonic bundles. And actually, there are some problems which appear only for harmonic bundles. But we can find many helpful ideas in the Hodge theory. And the second issue is to clarify the meaning of purely harmonic metric for harmonic D-modules. As I mentioned, purely harmonic metric is defined in the language of differential geometry. And at least naively, it is not so adapted to harmonic D-modules. And the answer is again given by Simpson's meta-theorem. It suggests we should have a twistor version of polarized pure Hodge modules. And that should be harmonic D-module with purely harmonic metric. And the concept was realized as a polarized pure twistor D-modules introduced by Claude Saba and developed by Saba and myself based on the theory of Hodge modules due to Morihiko Saito. And the third issue is we need a general theory concerning the structure of irregular singularities of meromorphic flat bundles. Meromorphic flat bundles are a special type of harmonic D-modules, but they are still singular. And to apply the differential geometric technique to such singular objects, we need a clean description of the singularity. And if the base space is one-dimensional, the classical theory says, after the formal completion and the pullback by unifying covering, we have a clean description of the singularity of meromorphic flat bundles. But in the high-dimensional case, we need an additional birational procedure called resolution of turning points. So for instance, we have these issues, and we will return to these issues later in this talk. And let me mention our main application. As I mentioned, our theorem implies, our theorem gives a useful characterization of semi-simplicity of algebraic harmonic D modules. And it also implies any semi-simple algebraic harmonic D modules are equipped with a very strong structure. So by using the characterization and the functoriality of the structure, we obtain the following theorem. So suppose we are given a morphism of complex projective manifolds. And suppose we are given a semi-simple harmonic D module on X. By general theory, we can consider the pushword of the harmonic D module M in the derived category of harmonic D module on Y. And by taking the cohomology shifts, we obtain harmonic D modules on Y, which is denoted by F dagger IM in the screen. And then our theorem says they are also semi-simple. And the pushword is isomorphic to the direct sum of its cohomology objects in the derived category of harmonic D modules on Y. This was conjectured by Kashiwara, and this is a generalization of the celebrated decomposition theorem due to Beilinson, Bernstein, Green, and Gaba. So this is our main application, and we will return to this theorem later in this talk. Okay, so in the following, first we recall what is harmonic bundle, and then we shall describe the study of singular harmonic bundles or harmonic bundles with singularities, and then we will mention something about twistor D modules and some applications. So let me remind you a definition of harmonic bundles. We consider a semi-Philly vector bundle with a Hermitian metric on complex manifolds, equipped with the differential operators del bar and del E, and the Shea-Infinity sections theta and theta dagger, such that del bar plus del E is a unitary connection, and theta and theta dagger are mutually adjoint. Then, this tuple is called harmonic bundle if this condition is satisfied. This condition means the square of each operator is 0. And the operators are mutually commutative, except for the last relation, which is called Hitchin equation. This is one definition of harmonic bundle. And in this definition, the condition is given in quite symmetric way. But actually, it is not so easy to deal with this condition directly. So usually, we regard harmonic bundle in different ways. Namely, harmonic bundle is equivalent to Higgs bundle with a pure harmonic metric. And it is also equivalent to flat bundle with a pure harmonic metric. I mean, so if we pick del E bar and theta from a harmonic bundle, then they satisfy the condition, the vanishing condition there, del E bar, the square of del E bar 0 and del E bar theta equals 0 and theta square equals 0. And it means del E bar is a holomorphic structure of the vector bundle, and theta is the Higgs field of the holomorphic bundle. So we obtain a Higgs bundle from a harmonic bundle. And we can recover del E and theta dagger from del E bar and theta and the metric, because del E bar plus del E is a unitary connection, and theta dagger is the adjoint of theta. So if we fix del E bar and theta, we can regard the vanishing condition for del E and theta dagger as a condition for the metric. Actually, it is described as a nonlinear partial differential equation for the metric. And if the condition is satisfied, we say the metric is a pure harmonic metric of the Higgs bundle. So in this sense, harmonic bundle is equivalent to a Higgs bundle with a pure harmonic metric. Similarly, we can introduce the concept of pure harmonic metric for flat bundle. and harmonic bundle is equivalent to a flat bundle with a pure harmonic metric. So they are equivalent by definition. So in the following, we will not distinguish them. Let me mention some basic example. So we have the harmonic bundle associated to a holomorphic function. The Higgs bundle is given by the product line bundle and the differential of the function and the metric, trivial metric. And the harmonic bundle is equivalent to the flat bundle with the pure harmonic metric given by the product line bundle and the connection d plus df and the metric given like that. And let me mention this type of flat bundle and Higgs bundle naturally appears in the study of the Landau-Ginzburg model in the mirror symmetry. And I don't explain the detail here, but the study of harmonic bundles and mixed twistor D modules seems useful in the study of the quantum D module associated to the Landau-Ginzburg model, in particular in the study of their degenerations. Another basic example is given by flat bundle with a flat metric. This is rather easy and trivial example. And more important and more interesting example are given by polarized variation of complex Cauchy structure of weight n. This is a well-known generalization of the original concept of polarized variation of Cauchy structure of weight n. And it consists of vector bundle with grading and a flat connection satisfying the Griffith transversality with respect to this grading, and flat pairing, which is Hermitian or anti-Hermitian according to the parity of the weight, such that the decomposition is orthogonal with respect to the pairing, and the restriction of the pairing to the direct summands are positively definite after the twisting of the signature like that. And in this case, this positive definite metric is a pure harmonic metric of the flat bundle. Pure harmonic metric of the flat bundle. So in this way, polarized variation of complex Cauchy structure naturally induces a harmonic bundle. And they are very important and non-trivial and important examples in the study of harmonic bundles. So I cannot omit the most fundamental results in the study of harmonic bundles. So as I mentioned, by definition, any harmonic bundle has the underlying Higgs bundle and the underlying flat bundle. And for conversely, to construct a harmonic bundle from a given Higgs bundle or a given Higgs bundle, we have to solve a nonlinear partial differential equation for pure harmonic metrics. And in general, it is quite difficult, and even the existence of solution is not clear. But if the base space is projective manifold, then we have the correspondence of harmonic bundles and flat bundles and Higgs bundles. The correspondence of Corrett has already appeared in the introduction of this talk. And the correspondence of Simpson is also very important, which states Higgs bundle on projective manifold admits a pure harmonic metric if and only if it is polystable and its chunk characters are trivial. Maybe I should mention if the base space is one-dimensional and the rank of the vector bundle is 2, there are previous related work due to Dieterich-Osawa and Donaldson and Hitchin. In particular, the perspective of Hitchin related to this correspondence has been quite influential in the whole mathematics, not only in the study of harmonic bundles. So anyway, we can appreciate the theorem in various ways. For instance, it gives a surprising relation of the concepts in algebraic geometry and differential geometry. And it also gives a surprising relation of the solvability of nonlinear partial differential equation and algebraic geometric condition or categorical condition. And it is also interesting, the theorem came from two different research areas in global analysis. One is the study of harmonic maps, and the other is the study of the Kobayashi-Hitchin correspondence for vector bundles. Harmonic maps are critical points of the energy functional on the space of maps between Riemannian manifolds, and which generalizes the concept of geodesics and minimal surfaces and harmonic functions. And the existence of harmonic maps has been studied intensely by many people, and there are many useful research, many useful results, such as the classical theorem of Ilse-Sampson. And there are also useful techniques, such as the Bochner type technique of Shu, which says under some natural assumptions, harmonic map satisfies much stronger conditions. And Correct introduced his concept of harmonic metric as a twisted version of harmonic map to the symmetric space of Hermitian metrics. And he studied the existence theorem and the Bochner type technique for harmonic metrics. And he arrived at his correspondence of harmonic bundles and flat bundles on projective manifolds, or more generally compact scalar manifolds. And the Kobayashi-Chen correspondence for vector bundles is the equivalence of the existence of Hermitian metric and polystability conditions. It goes back to the correspondence of stable bundles of degree 0 and irreducible unitary flat bundles on compact Riemann surfaces, which is due to Narashima and Sejadori in 1960s. And in the high-dimensional case, Kobayashi introduced the concept of Hermitian-Einstein condition, and Kobayashi and Lübke proved vector bundle with Hermitian metric on projective manifold is polystable. And after the breakthrough work of Donaldson, and converse was established by Donaldson and Uhlenbeck and Yao. And Simpson generalized this to the Higgs case, inspired by the work of Hitching and motivated by his subject variation Hodge structure. And he also observed, under the vanishing of the Chern characters, Hermitian metric is automatically polyharmonic metric if the base space is projective. So in this way, he arrived at his correspondence of harmonic bundles and Higgs bundles. So anyway, such confluence of two research areas are also very interesting and fantastic to me. And as I mentioned in the introduction, the theorem implies many flat bundles and many Higgs bundles are equipped with a very strong structure. And it also implies the modular spaces of Higgs bundles or flat bundles have very special structures, such as hyperkähler structures or non-abelian Hodge structures. And on the basis of these facts and these structures, many interesting studies of many interesting applications are given, but I cannot explain them anymore here. Okay, and then the study of harmonic bundles is roughly divided into two branches. One is the study of modular spaces, and the other is the study of harmonic bundles with singularities. And precisely, it's not so appropriate to divide like this, because, for instance, the modular space of harmonic bundles with singularities on compact curves is intensively studied by Philip Borge. But anyway, in the rest of this talk, we will report the development in the study of singular harmonic bundles and something related. Okay, so we are interested in harmonic bundle with singularity, which means harmonic bundle given on the complement of normal crossing hypersurface. And we regard the hypersurface as the singularity of the harmonic bundle, or singular set of the harmonic bundles. Precisely, we don't have to assume these normal crossing hypersurface, but practically we assume it. And we remark, we don't study completely general harmonic bundle. It is not productive. Instead, we should introduce some conditions on the behavior of harmonic bundles around the singularity. The conditions are called wideness and tameness. And wide harmonic bundle is more general than tame harmonic bundle. And we study wide harmonic bundles. Let me explain the condition. So we consider a harmonic bundle given on X minus D, and X is a complex manifold, and D is a normal crossing hypersurface. And we have the Higgs bundle underlying the harmonic bundle. And the Higgs bundle induces a coherent shift on the cotangent bundle of X minus D. And the support of the coherent sheaf is called the spectral variety. Then the harmonic boundary is called tame if the closure of the spectral variety in the logarithmic cotangent bundle is proper over X. And the harmonic boundary is called wild if the closure of the spectral variety in logarithmic cotangent bundle twisted by OND is proper over X. For instance, the harmonic bundle associated to a meromorphic function is wild, and the harmonic bundle associated to a polarized variation of Hodge structure is tame. Then, the study of wide harmonic bundle or harmonic bundle with singularities is divided into two parts. One is concerned with the global structure of wide harmonic bundle, a global property of wide harmonic bundle, when the base space is projective. And the other is concerned with the local property of the harmonic bundle around the singularity. And in the global theory, the goal is rather clear. It is a generalization of the correct Simpson correspondence and the characterization of the semi-simplicity of Bellman-Flat bundle. But in the local theory, the goal is not so clear at first. So we should ask what we can show in the study of the singularity of harmonic bundles. We need a guiding principle for the study. And it is given by Simpson's meta-theorem, and I will explain it in the text. So Carlos Simpson introduced the concept of twistor structure, and he proposed a principle which sets any theorems and objects concerning Hodge structures should have their counterparts in the context of twistor structures. Twistor structure is a generalization, twistor structure is a holomorphic vector bundle on P1, and it is a generalization of the concept of Hodge structure. Let me remind you, complex Hodge structure is a C-vector space with two filtrations. And a vector space with one filtration induces a free C lambda module by the least construction. And so it gives a vector bundle, a direct vector bundle on spec C lambda, I mean a complex line. So we can easily observe if we are given two filtrations, they induce a vector bundle on P1. And the vector bundle is also equipped with naturally induced sheath action. And Simpson discovered this procedure induces equivalence of complex Hodge structure and twistor structure with sheath action. So in this sense, twistor structure is a generalization of complex Hodge structure. And he proposed a principle, any theorem and objects concerning Hodge structure should have their counterpart in the context of twistor structure. Actually, many concepts concerning Hodge structures can be easily generalized. For instance, twistor structure is called pure of weight M if it is isomorphic to the direct sum of OP1M. This is the twistor version of pure Hodge structure. And a mixed twistor structure is a twistor structure with an increasing filtration such that the filtration is exhaustive and the mth graded pieces are pure of weight M. So this is the twistor version of mixed Hodge structure. And tail to twist, we can also generalize tail to twist and polarization appropriately. And then Simpson introduced the concept of polarized variation of pure twistor structure, which is a twistor version of polarized variation of pure Hodge structure. And he discovered it is equivalent to harmonic bundle. Equivalence is given as follows. So from a harmonic bundle, for any non-zero complex number lambda, we have the flat connection obtained as the sum of del E bar and lambda theta dagger and del E and lambda inverse theta. So we have the family of flat connections parameterized by C star. And in general, it is not extended across lambda equals 0 and lambda equals infinity as a family of flat connections. But if we multiply lambda to the boundary part, we obtain the family of the differential operator given like that. And it is naturally extended across lambda equals 0. And the operators are not flat connections in the ordinary sense, but they are twisted version of flat connections, and they are called flat lambda connections. So we can extend the family of flat connections across lambda equals 0 in a twisted way. And similarly, we can extend the family across lambda equals infinity in a twisted way, but exchanging the roles of the holomorphic structure and the anti-holomorphic structure. So in this way, we obtain something on P1 times X. And that is variation of twistor structure if we give a precise formulation. And in this way, harmonic bundles and polarized variation of pure twistor structures are equivalent. So this discovery is very important because it suggests the study of polarized variation of Hodge structure can be a useful model for the study of harmonic bundles. And actually, it was very useful in the study of the local property of wide harmonic bundle around their singularities. Let me remind you two important results in the study of the singularity of polarized variation Hodge structure. One is the existence of the Hodge filtration on the Doreen extension. Polarized variation Hodge structure consists of flat bundle and Hodge filtration and the polarization. And according to the general theory, a flat bundle given on the complement of a normal cosine hypersurface is canonically extended to a vector bundle with a logarithmic connection on the whole space, and which is called Doreen extension. And according to the nilpotent orbit theorem of Schmidt, the Hodge filtration is extended to a filtration of the Doreen extension. It briefly means polarized variation of Hodge structure given on X minus D is naturally extended to a meromorphic object on X. And the other important result is the existence of limit polarized mixed Hodge structure at every point of the singularities. It briefly means the meromorphic object associated to the polarized variation of Hodge structure has very nice structure along the singularity. And we have generalization of these results in the context of harmonic bundles, which we call prolongation and reduction. And maybe they look rather technical, but let me explain them very briefly. So we consider wide harmonic bundle on XD, which means harmonic bundle given X minus D satisfying the wildness condition along D. Then, as I mentioned, we have the associated variation of pure twistor structure on X minus D. It is something P1 times X minus D, but we regard it as an object of X minus D. And our theorem says it is naturally extended to a meromorphic variation of twistor structure on X. Unfortunately, it is not easy to explain the precise meaning of this theorem, but let me remind you, we have a family of flat bundles on X minus D, and we also have the family of flat bundles. So we have the family of lambda flat bundles on X minus D, and the family of lambda inverse flat bundles on the conjugate of X minus D. And the theorem implies they are extended to family of meromorphic lambda flat bundles on X and the family of meromorphic lambda inverse flat bundle on the conjugate of X. And their Stokes structure and the Kelvin structures along the singularities are the same. So in that sense, they give something on P1 times X, and that is a meromorphic variation of twistor structure if we give a precise formulation. Here, Stokes structure is a family of locally given filtrations which control the growth order of the flat sections. And the KM structures is a family of locally given filtrations and the decompositions of the singularities, which control the growth order of harmonic sections and the residue of the connections. So anyway, in some appropriate sense, wide harmonic bundle is extended to the whole space, meromorphic object for the whole space. And here, let me remark, we can consider the associated graded object with respect to the Stokes structure and the KM structure. As I mentioned, Stokes structure and the KM structures are family of locally given filtrations or locally given filtrations and decompositions. So if we take the associated graded objects, we obtain family of locally given objects. But we can group them in canonical way, and we obtain some global objects. So in that sense, we can consider the associated graded object with respect to the Stokes structure and the KM structure. Then we obtain the following sequence of reductions. So starting from wide harmonic bundle, by taking the grading with respect to the Stokes structure, we obtain KM harmonic bundles. And then by taking the grading with respect to the KM structures, we obtain polarized mixed twistor structure. And then moreover, by taking the grading with respect to the weight filtration of polarized mixed twistor structure, we obtain polarized mixed host structure. And we can understand the polarized mixed host structure very well because by the work of Katanika-Schmidt and Kashiwara-Kawai. And in this sequence of reductions, the reduced objects give a very useful approximation of the original one. So we can reduce some issues for wide harmonic bundles to the issues for simpler objects. So in that way, we can understand the local structure of wide harmonic bundles around singularity. And we can say the meromorphic object associated to a wide harmonic bundle has a very nice structure along the singularities. So this is main result in the study of the local property of wide harmonic bundles. And for the global property, after the work of many people, we have satisfactory generalization of the correct Simpson correspondence and the characterization of semi-simplicity of meromorphic flat bundles. I don't explain who did what, but and for the generalization of the correct Simpson correspondences, we have to consider a kind of boundary conditions called parabolic structure. So we have the correspondence of meromorphic flat. We have the correspondences of wide harmonic bundles and meromorphic flat bundles with parabolic structure, and meromorphic flat bundles with meromorphic Higgs bundles with parabolic structures. And precisely, we have to introduce characteristic numbers for parabolic objects, and we have to introduce the stability condition for parabolic objects. And moreover, we have to consider we have to impose some conditions along the singularities. But I missed such detail here. And for the characterization of semi-simplicity, we have the following theorem. So meromorphic flat bundle on projective manifold is semi-simple if and only if it comes from √-1R wide harmonic bundle. Here, √-1R means the eigenvalues of the residue of the associated Higgs fields are purely imaginary. And comes from means it is obtained by the procedure of prolongation explained in the local theory. But so anyway, so let me mention a problem in the proof of this theorem. We use, for the construction of real harmonic metric, we use a classical technique of heat flow in global analysis. I mean, first we take an appropriate and initial metric and of the smooth part of the metric, smooth part of the meromorphic flat bundle, and then we deform it along the nonlinear heat flow associated to Hermitian-Einstein condition. Then the limit of the flow should be the desired purely harmonic metric under some natural assumptions. This is a classical framework in global analysis. And Simpson established a very useful theorem for this procedure. But to apply this method, we have to, in the first step, we have to take up appropriate initial metric which should satisfy some finiteness conditions and which should be adapted to the meromorphic boundaries. And to construct such appropriate metric, we need a clean description of the meromorphic boundary. I mean, clean description of the singularity of the meromorphic boundaries. And in the in the high-dimensional case, if the base space is high-dimensional, then in general there is a very bad point at which we don't have a clean description in a naive sense. So we have to find a birational transform by which we can eliminate such bad points. That is called resolution turning points. Let me mention something more about this issue. So the classical concept of Hooke's type singularity of ordinary equation was generalized to regular singularity of meromorphic boundaries and well established by the work of Dorigny. And for the irregular singularity, if the base space is one-dimensional, there is a well established and very useful classical theory. And rather recently, we obtained a higher dimensional generalization of the classical theory after the work of many people. And let me remind you, the classical theory in the one-dimensional case consists of three main results. One is the existence of the decomposition into the direct sum of regular singular meromorphic boundaries twisted by meromorphic functions after the formal completion and pullback by unified covering. That is called Foucault-Lebet Turretin decomposition. And second is the existence of flat decompositions on small sectors which are adapted to the Foucault-Lebet Turretin decompositions. They are given by the method of asymptotic analysis. And such decompositions are not unique, but the ambiguities are controlled by the Stokes structure. And third step is a generalization of, third step is a classification of meromorphic boundaries in terms of the Stokes structure and monodromy, and which is attributed to Dorigny and Malgrange and Shibuya. This is a classical theory in the one-dimensional case. And in the high-dimensional case, it turned out we need one additional step. Namely, in general, there are very bad points at which we don't have the Foucault-Lebet Turretin decomposition only after the formal completion and the pullback by unified covering. But our theorem says, at least in the algebraic setting, we can find appropriate blow-up by which we can eliminate such very bad points. That is called resolution turning points. And the existence of resolution turning points was conjectured by Claude Sabat and proved by Kiran Kedoria and myself in algebraic case. And I should remark that the result of Kedoria is more general. And let me mention, this generalization is very useful in the study of meromorphic boundaries. Actually, it was used in my proof of the characterization of semi-simplicity of meromorphic boundaries. And more recently, it is efficiently used in the study of generalized Riemann-Hilbert correspondence due to Kashiwara and Daniel and Kashiwara. Okay. So let me remind you, I mentioned three issues in the introduction, and we have already discussed the first and third issues. And the second issue is to clarify the meaning of pre-harmonic metric for harmonic D modules. And as I mentioned, twistor version of polarized variation Hodge structure is harmonic boundary, that is flat bundle with pre-harmonic metric. And we have the D-module version of polarized variation Hodge structure, that is polarized pure Hodge module due to Morihiko-Saito. And according to Simpson's meta theorem, we should have a twistor version of polarized pure Hodge module, and that should be the D-module version of harmonic bundle, which is harmonic D module with pre-harmonic metric. And the concept was realized as polarized pure twistor D module. Let me measure something more about twistor D modules. It is valuable to consider additional structures on harmonic D modules or perverse sheaves. Such a study was invented by Beilinson, Bernstein, Dorin, and Gaba, who developed the theory of perverse sheaves with Frobenius action on algebraic varieties of a finite field. And as a counterpart in the complex geometry, Morihiko-Saito introduced and established the theory of mixed Hodge modules, which are roughly regular harmonic D module with mixed Hodge structure. And I'd like to emphasize his work is highly original and really excellent and done by his genius. And the twistor D module is a twistor version of Hodge module. The study of twistor D module was initiated by Claude Saba and developed by him and myself on the basis of the theory of Hodge modules. And let me emphasize, Saba made various innovations when he gave a foundation of twistor D modules. The ingredients of Hodge module and twistor D modules are not the same, so he made various innovations. And it is necessary to consider, it is necessary to apply the study of irregular singularities. But anyway, so there are two main results in the study of twistor D modules. One is concerned with the functoriality. In the pure case, we have the Hard-Lecture theorem, which I will explain later. And for the mixed twistor D modules, we have 6 operations of Grothendieck, and the nearby cycle functor, and the vanishing cycle functor, and the duality. And the second main result is concerned with the description of twistor D modules. Pure and mixed twistor D modules, the definition of pure and mixed twistor D modules are very complicated. So we need a more general, more convenient description. And in the pure case, our theorem states polarizable pure twistor D modules are the minimal extension of variation of polarized pure twistor structures associated to wide harmonic bundles up to the sixth of the weight, which briefly means we have natural correspondence of wide harmonic bundles and polarized pure twistor D modules. And in the mixed case, mixed twistor D modules are locally obtained as a grouping of administrative variation of mixed twistor structures. So I don't explain them so carefully. And let me explain something more about Hard-Lecture theorem. Let me begin with some special cases which is due to Simpson. So we consider a harmonic bundle on a complex projective manifold with an amp-line bundle. And we consider the drum cohomology of the flat bundle underlying the harmonic bundle. Then we have the morphism like that, given by the multiplication of the first Chern class of the line bundle. And Simpson proved they are isomorphisms by generalizing the argument of Dorin in the Hodge case. And we also have the case of generalization of the smooth family case. I mean, so suppose we are given a smooth morphism of projective manifolds. Then, if we by considering the drum cohomology group of the restriction of the flat bundles to the fibers, we obtain flat bundles on the space Y. Then, the morphism induced by, like that, induced by the multiplication of the first Chern class are isomorphism. And moreover, in this case, by considering the harmonic forms of harmonic bundles, we have an induced Hermitian metric on the flat bundles. And Simpson proved the Hermitian metrics are pre-harmonic metric. It means the push forward of flat bundles by smooth projective morphism is enriched to the push forward of harmonic bundles. And our theorem is a generalization of this. So suppose we are given any projective morphism with a relative unprime bundle L. We don't assume this is smooth morphism. And suppose we are given a polarizable pair twistor D module on X. And we have the underlying harmonic D module denoted by M. And by considering the push forward and taking the cohomology shifts, we obtain the harmonic D modules on Y denoted by F plus IM. Then our theorem set implies we have a naturally induced polarizable pair twistor D modules and whose underlying harmonic D modules are F plus IM. So it means the push forward of harmonic D modules by projective morphism is ended to the push forward of polarized group twistor D modules. And moreover, the morphism are from F diagonal Jm to F plus Jm induced by the first chunk of L are isomorphisms. This is a generalization of the theorem of Simpson and Doreen, but the method is essential. The most essential ideas of this theorem is due to Saito. Okay, so now we return to the theorems mentioned in the introduction. So, as I mentioned, we have the correspondence of semi-simple algebraic melon flat bundles and √-1 wide harmonic bundles on projective manifolds, which is the characterization of semi-simplicity of melon flat bundles on projective manifolds. And we also have the correspondence of wide harmonic bundles and polarizable pair twistor D modules. I mean, as I mentioned, polarized pair twistor D modules are minimal extension wide harmonic bundles up to shift of the weights. So by getting them together, we obtain the correspondence of semi-simple harmonic D modules and √-1R polarizable pair twistor D modules on projective manifolds. That is the characterization of semi-simplicity mentioned in the introduction. And and by using the characterization and by using the functionality of the polarizable pair twistor D modules, we obtain the following theorem. So suppose we are given a semi-simple algebraic harmonic D module on complex algebraic manifold. And if we are given a projective morphism of complex algebraic manifold, then the cohomology of the push forward of the semi-simple harmonic D module are also semi-simple. And moreover, the push forward is isomorphic to the direct sum of its cohomology object in the Jobs category. And moreover, for any algebraic function on X, the graded pieces of the nearby cycle sheaf and the vanishing cycle sheaf with respect to the monodominate filtrations are also semi-simple. And this was conjectured by Kashiwara, and this is a generalization of the more important results of Beilinson, Bernstein, Turin, and Gaba. They proved this kind of theorems for regular harmonic D modules of geometric origin. They used the method of monopy reductions and the theory of Harvard shift with Frobenius action on algebraic varieties of finite fields. Of course, they also used the Riemann field correspondence due to Kashiwara and Meibuk. And their result was vastly generalized by Moriko Saito, who proved this kind of claim for regular harmonic D modules underlying polarizable pair Hodge modules. And it was generalized for semi-simple regular harmonic D modules by two methods. One is given by the method of arithmetic symmetry, which is due to Drinfeld, Beckel, Kare, and Kaitskori. And the other is given by the method of twistor D modules and table harmonic bundles, which is given by Saba and myself. And so in the contrast, and Cataldo and Migliori gave another proof of the case of geometric origin by using the Hodge theoretic method. But and on the contrast to the previous results, our result is in our theorem we removed the assumptions of regularity. That is a new point from the previous results. Okay. So finally, let me mention some recent studies. So we have some application of the theory of harmonic bundles. For instance, some type of harmonic bundles appears as a solution of the two-dimensional total equations. And we can classify them, and we have a criterion when the associated Melon flat bundle has an integral structure. This is related to the work of Guest and Itz and Lin, and it seems useful in the study of the T-twistor geometry by physicists Chekotky and Vaha. And it turned out the local theory of wide harmonic bundles seems foundational in the study of some type of instantons and monopoles. This is related to the work of Vicar and Marcos Jardin on the doubly periodic instantons. And more recently, I'm interested in the application of the theory of mixed twistor D module in the study of degeneration of quantum D module associated to Landau-Ginzburg models. It is related to the work of Konishi and Minabe and Reichelt Sevenek. And this kind of constellation leads to us a systematic study of the mixed twistor D module associated to Melmorphic functions. It is related to the work of Eno and Saba and Yu and Saito on the Konsevich complexes. So let me mention something about Konsevich complex. So Konsevich and Eno and Saba and Yu and Moriko Saito studied a family of complexes, and they found very interesting results, which says the dimension of the hypercohomology group are independent of the parameter. And we can revisit this theorem from the viewpoint of the twistor D modules. I don't explain the detail, but so first we can interpret the complex, a part of complex as the relative term cohomology of the D module, like that, sorry. And by using the functoriality of the V federation, we obtain a part of the theorem. And we can enrich this argument by mixed twistor D modules. And then we can obtain the full claim of the theorem. Okay, so I'll stop here. Thank you very much.
Thank you very much for your lecture on such deep and beautiful mathematics. Are there any questions? Well, if not, let's thank Professor Mochizuki again for his wonderful lecture.